welcome back everybody. In my talk here, I will conclude the talk about the digital part, and in particular in this tutorial, the lecturer will talk about some algorithms that are present in YAML that help to increase the accuracy and the speed up of the GW computation. If until now in the previous lecture, you have seen that the parameters converge, and these parameters are the ones to check always the same for systems. In the algorithm here, I will show you can depend on the material. If for certain materials, you can adopt a certain algorithm that helps increase the speed up, while for other materials, you cannot use the same algorithm. So, I think quantities you will always check. So it's not something that is for each case you should consider what you should do depending on the material and also on the energy control. So what are the things you want to get? Particular, we'll keep it connected. No. So the quantities I will stress about will be about the frequency dependence, and very correctly show what are the problems in dependence, and I will introduce how numerical methods, and then very briefly, and then we'll pass to the analytical methods, one of which I already seen in the reflector is the Flavian Fourier. And the second part, we will talk about the momentum dependence, and I will show what's the need, what are the issues, and I will illustrate it using the case of 2D systems. So just show sum up. Now you should be kind of familiar with the G0W0 processing, the things you do. The first thing you compute is the reducible for reusability. Then from this you can solve the matrix. Then you can find the screening potential, and from this you can finally compute the self-energy, in which you see the product between the single particle propagator and the potential. And this is all integrated in space, in the space representation. But if you pass in the momentum representation, you have a double integral of the frequency and the momentum. And for certain elements, you also need to consider all the Cornishian states. And if you remember, like in the lemma representation, G0 features Cornishian energies, while the boundary potential is in the wave function, the plane wave set depends on G prime, and then we need to transform it back to the wave function. So this the expression seems kind of simple here, but okay, computation is not so very important. In particular, because it's present in double integrals of frequency and omega. And okay, in this case, the frequency scales linearly. The momentum with the dependency is worse. But if you remember, within the spring potential W, there is a chi, or there is another integral of Q. The dependency is even worse. So now I will focus on the frequency dependence. So let's look again at the propagator. Now you are the lemma representation, propagator, there are the poles of the Cornishian energies, and these respective Fermi energies either lie above or below the field. So the propagator is a sum of poles. What about W? Well, W is also sum of poles. It's not as straightforward as P0 to the fact that now we need to consider all the possible transition energies between a certain Cornishian state to another Cornishian state. So you see the number of poles of W can be quite large. And indeed, we want to solve the energies, you will have a lot of poles of the poles of the propagator and all the poles of the critical potential. And this is the integral you should solve just frequency. And okay, Professor Gavoni before showed you a way to solve this through like a linear continuation with integration with using Cauchy theorem. There is another way to solve this, for example, the one that is a way to solve this numerically is the one used by Young, in which you do an exact configuration along the real axis from 0 to infinity. And basically what you do is you divide this real axis in a lot of intervals, you compute W at the edges of the intervals, and you assume like a linear behavior of W within the interval. So you can plot this numerically. It's very computational demanding because like you want to solve in a good way this W, where this set energy, you need like more than 150, 300 frequencies. So you see it's an order of magnitude, 2 order of magnitude more on top of already unexpected. And that's the reason for which we don't like to do this. Like we want to avoid this. That's the reason which we stick with the analytical approach. The one started before is a plasma polar approximation. There is another one in the So in the plasma polar approximation, you exploit the physics of the system. You know that if you do an NIRS experiment, the peak of the response of a material will be at the plasma energies. In particular, so epsilon macroscopic -1 will show peak here. And so basically what you want to try to describe the behavior of the system just using this plasma frequency. So this is a collective station of the light. So you assume that for all frequency, in all the frequency, for all the energies, you can treat epsilon -1 just using this plasma frequency. Okay, these are the expressions, basically have plasma frequency, and this is the resonance. And if you do the computation, we can have that one way of determining the two quantities. Strictly speaking, this relation here is for the macroscopic part of the function. But Iverson and Louis showed in 1986 that actually you can use this relation also for the microscopic component of the dielectric matter. So you use the strategy, plasma strategies, not just for the 0-0 elements, but for all the elements, for all the G and G prime factors. So for all the elements, you apply this strategy. Okay, in particular in the Albertson and Louis model, they determine these two parameters, R and omega prime, omega the plasma, just using one sampling frequency. In Yango, actually, we don't use this Iverson and Louis strategy, use a slightly different strategy, that is the Godby-Mix model. But okay, they're the same. Basically, we use, in this case, two sampling frequencies, one at 0, the other at typically set along the imaginary axis at 1/3. And imposing these two relations here, we can find the two parameters needed for the plasma point. And we can compare like the Godby-Mix model with the Iverson and Louis model and with the exact numerical integration. The one you can obtain with a real integration. And you see the two compare very well. Actually, Godby-Mix model to other control model is the one that performs best for the first particle energies and to describe the behavior of the electric function. Numerical integration and experiments may, however, disagree since we are still in the GW approximation. So what is the reference here for the Godby-Mix model should map in the numerical integration. And you see, so the results are very satisfactory. So it seems we are fine, or at least for all materials, plasma models very good. It's on par of the full frequency approach. So, however, it's not always the case. There are cases in which, in fact, plasma model has limitation. In particular, its performance tends to worsen as you move away from the free energy. And it has problems, in particular, dealing in systems where W cannot be approximated by a single peak, but actually W may have more than one peak. For example, here, you see that the behavior of W is very complicated in frequency. There are a lot of peaks, and if you use the plasma polar approximation, you just end up with a single peak that is more or less in correspondence with the same one you find with the biggest one, the full frequency approach, so with the exact numerical integration. But you see, it's not very satisfactory, this representation of W with the plasma in this case here. There are other techniques and the other analytical models that can improve the agreement with the exact numerical integration. For example, it is the strategy by the multiple approximations that will show just after. Another way to understand the failure of one pole estimation is in the case that if you look, for example, at 2D metal. In a 2D metal, expect the presence of two plasma peaks that are either associated to interband transition, that is a higher energy, and a lower energy peak associated to interband transition. And if you use the plasma core approximation, you can either describe this peak here or this peak here, depending on your choice of your sampling frequency. But if you want a precise description of, well, the quasi-particle interaction, you actually need to include both. That's really which you are using a model is not enough for what the system actually is. And that's the reason for which in YAML it's been introduced another approach, another analytical approach is the multiple approximation. The idea is you want to, and it's just an extension, you can look at it of the plasma core approximation. Instead of considering just one collective motion of the electrons, you are allowing the system to be more than one collective motion. A lot of these collective still, there are not as many as a single particle transition, but you allow the presence of a finite number of collective motion, is a NP, for example. And to determine the frequency of this collective motion, you need 2 to the number of modes, 2 to the number of modes you want to consider, so 2 to the NP, 2 times NP. And so for all these couples of like sampling frequency, because this the strategy you can like explore the complex plane to determine these modes here, you will for all these couples you can find an associated values of energy of the collective motion and the residue of the collective motion. So this expression is exactly the same of the plasma pole, but instead here we are summing on NP instead of just considering one. And another difference is that these collective modes can be complex. Instead, in the plasma pole models, they are it's always real. So, but you see now we are exploring a large region of the frequency space. So now we have less dependence on the sampling choice. That can be an issue instead for the plasma pole. I show you depending on like which sampling you choose. In certain materials you explore like either low energy modes or high energy modes. Instead here we have a continuous exploration in a larger energy. So this is nice. So I think like multipole improved the agreement on with analytical modes and then with exact numerical integration techniques. And we can look at the result, for example, in the case of semiconductors and insulators. Okay, in semiconductors like silicon, already the plasma pole works quite well, so we don't have a real large scale in this case. But for example, another insulator like HBN, there is some difference between the plasma pole and the frequency. Instead, the multipole basically are the same results. In a metal, the improvement is even better, and you can see that the frequency and pole are basically of the same order of magnitude. Instead of like the exact numerical integration and the plasma pole, there's a difference that can amount to almost to like alpha NP, that is very hard. And okay, you can look at this plot here. This is the real part of the self energy. Remember, is the one there is the amount of the quasi-particle fraction. You see, like the two curves, the two superimpose one another. Instead, the plasma pole here is not so bad. Here instead, the difference is, and that's why it determines this difference, this magnitude. So you see, in general, these are system dependent. Like for silicon, totally fine across the board, even for other insulators, totally fine. For other materials, it's not really that to use other techniques. So these are all for the frequency dependence. We now pass to the second part that is about the momentum dependence. So now we are back to our integral. Now we have done this part here, but we still have to do the integral on the momentum. And this can scale very badly. And why is this? And to illustrate this, I take a very simple illustrative case that is the one of 2D system. I think now we are all familiar with systems. We basically have a layer of atoms that is infinitely expanding. Then instead of the direction, the vertical direction, it is at downside. It has no communication with this. But the communication between the layers, what you do is you increase the distance between the layers in your simulation to the vacuum size. And this is a convergence parameter. You need to do that. DFT. Okay, in the DFT computation, everything is fine. They're like the convergence of the vacuum and very fast between like 10, 15 nanometers. You are a convergence here. In many body calculations, that the trouble is much larger because like you need the vacuum, you need to use can be like ideally should be infinitely extended. And this is due to the fact that in all the quantities depend on the Coulomb interaction. The Coulomb interaction, by its nature, is long-ranged. And so, for a fully converged population, ideally, if you don't use an accelerated technique like truncation. The problem also lies in the fact that the dependence on the vacuum and on the K-mesh used in your simulation are not independent one another. You see, the convergence of these different curves depends on the grid. In this case, the convergence with respect to this grid is worse with respect to the one which uses a denser grid. So there is like you cannot split the two. There is like an interdependence. Typically, what you want to do, so you to use these truncation techniques. So basically, what you do is instead of using the Berg-Coulomb interaction, use a fitted form of the Coulomb interaction. You basically encapsulate the Coulomb interaction within your supercell, the simulation of your supercell, and you remove all communication between the different like monolayers. Problem, but it forces dependence on the degree, because if you use the Berg-Coulomb interaction, the convergence degree is around 30, something like that. Instead, here already like 45 times 45 is not fully converged. So really, we need a very large grid, and we don't want this. We want to like work with smaller grids. And there are techniques in YAML to like remove like finish this dependence of the grid. And the first one is the W average method, the BU average method. It is an exact integration of the Berg-Coulomb function. What this does can be understood looking at the Brillouin zone of your material in your simulation. Your Brillouin zone can be split in a different sub areas that are all associated to the different points of your K-mesh you're used in your simulation. So basically, you are splitting your Brillouin zone in different smaller integrated points. And within this area here, you do the exact integration of the Berg-Coulomb potential. Instead, the electric matrix epsilon and the propagator G, you keep them piecewise constant. With G, and that's one, you keep constant within all this region here that V is exactly integrated. And the integration in particular uses Monte Carlo integration. And this improves the efficiency, in particular, removes the problems of dealing with the queue, the long wavelength integration of the block tension. May, however, not be enough for all the materials, since in certain cases you cannot treat epsilon to the -1 as being piecewise constant. And in that case, you don't have to do an integration around the integration of the Berggruen potential. You need to do that integration of the Spring-Coulomb potential W. So the idea is exactly the same. Okay, this technique precisely is applied only in the conduction, in the correlation part of the search energy. But and you keep this quantity. So the other quantity, so keep only the single particle propagator as piecewise constant. Why is necessary? Well, you can look at this plot here by Berton. You see like certain parts of the dielectric matrix, like for example this line here, are indeed the piecewise constant for all the different momentum Q. Instead, other parts, like this green function here, is very sharp with respect to the momentum. So you cannot assume this as piecewise constant, and you need to integrate the whole thing together. The problem is that, well, when you do your simulation, you have an exact analytic value. You know the expression of the Spring-Coulomb potential only the points of your simulation, not in the whole Brian zone. Instead, for the Berggruen potential, you know the analytic force, like 1 over modulus Q plus G. So how can you reconstruct the analytic form of W? You need for the random integration method, but this is done using interpolation techniques. So consider, in your simulation, you have these big black dots, and you reconstruct the analytic form using interpolation between neighboring points. And so you end up with this orange curve here. And if you see the orange curve nicely superimposed on the denser grid, the 60 times 60, and you see the results composed very well, particularly in the correlation part of the Spring-Coulomb potential. And this has led to a dramatic speed up. I think you can see now the case of these semiconductors. If you use only the web average method, see a very slow convergence, especially with grid. Instead, the double average, the smallest grid, like 6 times 6, is already a convergence close to the extrapolated value. Now, this double average method has been applied to these semiconductors. What I'm working on is an extension of this double average method in the case of metals. Even in metals, there is a problem of the dependence on the Kipp grid, and this can be understood looking at this plot here. Now, if you remember, when you compute the electric function, you need to consider both all the transition from the valence to the conduction path. And in Yambo, there is no problem to consider all of them at finite momentum. If you, however, go to like zero transfer momentum, you need to consider transition between the points and to the point itself. So around Q equal to 0. And this is numerically not well defined. And that's the reason for which in this limit, only interband transition are considered, while the intra-band transition are removed. However, this is an issue since we are missing the Q equal to 0 limit of the interband transitions. That is rather important. So the idea in the double average method, in the case of metals, is to use the same technique. We completely remove the Q equal to 0 case, but we keep all the other elements, and we extrapolate the values going for Q equal to 0 based on the known physics of the metals. Well, in particular, we are linking the behavior of this extrapolating function to the reducible coherentability K0 that is a polynomial. And you see also in the small region here, there is a nice superimposition where we are extrapolating between the analytical result and the numerical result on the denser grid. This is for separating function for the screen clone. And okay, so I applied this degree for 3D metals, and this is the behavior of W for different transfer momenta Q. You see like the normal computation and the computation with the W average method superimposed at final momentum. Instead for Q equal to 0, normal computation at this broad peak that is equal to 0. Instead with the correct reconstruction, you find this here, that is actually the platform of the metals. And if you compare it with the experimental value, you see that the two agree very well. Now, there is actually a way to include the experimental value of the plastic peak, that is with the addition of a Drude peak, to the plasma energy. The problem is whether that is an input parameter. So if you start the computation, you may not know it, but if you know it, you can superimpose it at a certain energy. The problem is that, okay, this is a very simple case, that is the sodium. In certain other cases, you cannot define a single Drude peak. It may be possible that there are multiple Drude peaks. And in that case, this Drude method doesn't as well. And even in this case, you see that the acceleration provided by the double average method is very high compared to the standard computation. Here, in this case, the convergence basically is the smallest grid. So normal computation, even in this grid, is quite far off. And I use this method even in the case of 2D metals. 2D metals, the problem is worse because in this case, as I showed you before, we have two plastic peaks. One that is associated to interband transition, and the other that is associated to interband transition. And the one associated to interband transition is at small energy. And as you increase the moment transfer momentum, it vanishes off. So the interband transition has a less problem with the transfer momentum. And the double average method is able to reconstruct both the intraband peak and the interband peak. And even in this case, you see there is an improvement to the convergence. The improvement is not as drastic in this material graphene, as graphene is a bit of a problematic system to treat. My suggestion of what you should do for different systems, like if you're dealing with semiconductors, the plasma Paul approximation is in general fine. In certain cases, far from the Fermi energy, you may want more refined techniques of the frequency treatment. But if you're dealing with metals, but even semi-metals, in certain cases, you need more advanced techniques when dealing with the frequency dependence. And okay, this is a summary of this. So I'm open for questions.
Thank you very much, Giacomo. Questions? So let me add a comment of mine that is the following. The MPA approach that Giacomo has just presented that can actually be seen also in comparison with other methods that are published in the literature and available in the form of software, really as a exact full frequency approach which is applicable. So for instance, typically, the exact approach would be the contour deformation numerical approach to full frequency W, that is where the frequency convolution or in the calculation of the W energy is performed exactly. And here represents the frequency dependence in the complex plane of W as a standard force, and this is a rational representation that mathematically becomes exactly when you increase the number of forces. Since you have control over the number of forces that you use, that is indeed a reliable mathematical representation for the object that then leads to an exact treatment. So I think to an extent, MT can really be seen as a exact treatment of full frequency, plus the control of the number of poles.
My question was going to be spin following of the difference to the MPA and improve the program that.
Are there some other questions?
You could repeat briefly the difference between the average and the average.
Okay. Okay, in the p-average method, what you are doing a stochastic integration is of the Bergson potential, the one you always know that in form. So it's the 1 divided by Q plus, is like the standard Bergson potential, U divided by modulus Q plus Q. Instead, in the double average method, where you are doing an exact integration, is the one of W. The problem is that in general, of W, you don't know the analytic form. And you need an analytic form of W for doing this stochastic integration. And that's the reason for which we pass through this interpolating function that its only purpose for in this case is the one to determine an analytic form of W. And the analytic form, however, differs within all the different intervals, because what to do within all the intervals is a polynomial interpolation. So basically assume that you can treat these quantities here since are moved as some polynomials. And so by using the sum of polynomials, you can end up with an analytic form of W. So the difference is what you are doing an analytic exact integration and what you are keeping piecewise constant. Because when you're doing exact integration of B, what you're doing keeping piecewise constant is both G and infinity to the -1. Instead, when you're doing an exact integration of W to keep a piecewise constant is only G. Within all these different areas of within all different this subset of the Brilliant.
Understanding the post or the lights which refer to frequency integration. So could you please go back to that?
Do you mean like the plasma pole?
Because in the slide, frequency integration.
Ah, here.
Yes.
Ah, okay.
The one they put like this. Fundamental. Oh, yeah. Looks like that. But yes, I understand that you are calculating the poles. But
No, I am not. This is the lemma representation of the propagator. And you know that well, the poles of the propagator will be at the, okay, in this case, at the connection energies, because we have started with the identity computation. If you do another choice of starting point, we'll have the poles, like at the Newton theory you use as your starting point. So in this case, yeah, will be connection energies. But like these are the results of the DFT computation, the position of these poles here. And the poles of W will be at the difference between these two energies here, since within the lattice matrix, there are the single particle transition between a connection state to another connection state. So the poles in that case will be all the transition passing like from this point here, that point here, and so on and so forth. So all the transition energies. And that's the reason for which there is this complicated result with complicated pattern, which you have a lot of force. So this the result coming from your DFT, so your starting point.
How will you explain like poles which are farther from the axis to the nearer to that?
Yeah, this one is on what's your choice for the imaginary part. And as Claudia talked about before, it's a choice you make, like you introduce a damping quantity, it's called, and this is a parameter actually you should, like, is a choice you can control, but you cannot remove since you don't want this force here to be exactly on the real axis, otherwise you have complications. So improve the efficiency, like to remove numerical problems you introduce. a small imaginary part.
Okay, so any other questions?
And you remember, like, this propagator here is the retarded propagator. So this, why it is positive, is negative, associated effect with the retarded.